Hello everyone, welcome to Ops by Yash. Today we will be breaking down Docker architecture. You run one tiny command, docker run nginx, and boom, nginx is running. Seems simple, right? But behind that one command, Docker is basically calling half the family. The Docker CLI talks to the Docker engine, the engine talks to the container D works with runc, and eventually we reach the Linux kernel. So today we are going behind the scenes. We are going to understand exactly what happens when you run a Docker container, from the command you type all the way down to the Linux process that actually runs your application. And by the end of this video, Docker architecture should stop looking like this mystery black box. Now you might be thinking, you can already run Docker, why do I need to know all this? Because when everything works, architecture is boring. But when something breaks at 2 am, suddenly architecture becomes your best friend. Is the CLI failing? Is Docker engine is down? Did the image fail to pull? Is the container running but the application can't connect? Did the container hit its memory limit? Understanding the architecture helps you answer those questions, and that's especially important in DevOps and production environment. So here's the architecture we are going to follow. You use the Docker CLI. The CLI communicates through the Docker API with dockerd, the Docker daemon. Then we have container D, which handles container lifecycle operations. Then runc, the low-level container runtime. And finally, all of this relies on the Linux kernel. The kernel provides things like namespaces, cgroups, file system isolation, networking, and process management. So don't worry. If this looks like a lot right now, we are going to break every single piece down. Let's start with something familiar. Suppose we run this command. What do we actually expect Docker to do? First, find the nginx image. If it doesn't exist locally, get it from the registry. Then create a container from that image, set up its file system, configure networking, apply resource and isolation rules, and finally start the nginx process. So when you see Docker run, don't think Docker starts a container. Think Docker starts a whole workflow. So first we have Docker CLI. This is the part most developers interact with. When you type docker run nginx, the CLI understands that command and converts it into an API request. And here is an important distinction. The CLI doesn't actually create your container. It's basically the messenger. Think of it like ordering food. You tell the waiter what you want, the waiter sends the order to the kitchen, the waiter doesn't cook your biryani. Similarly, the Docker CLI doesn't create the container itself. It sends the request to the Docker daemon. So how does the CLI communicate with the daemon? Through the Docker API. The API is essentially the communication contract between the Docker client and Docker daemon. The CLI sends a request, the API carries that request, and the daemon performs the action. This separation is important because the client and daemon don't necessarily have to be sitting on the same machine. You can have a Docker client communicating through a remote Docker daemon. So remember, CLI is the interface, API is the communication layer, and daemon is one doing the work. Now we reach the Docker engine, specifically the Docker daemon, dockerd. This is a coordinator. It manages high-level Docker operation. Images, Docker manages them. Container, Docker creates, start and stop them. Networking, Docker sets that up. Storage, Docker manages that too. So you think of dockerd as the manager sitting in the middle saying, okay, I got the request, let's make this happen. But here's the interesting part. Dockerd doesn't do every low-level operation itself. It delegates some of that work further down the stack. Before Docker can start nginx, it needs the nginx image. Docker first check its local image store. If the image already exists locally, great. No need to download it again. But if it is missing, Docker needs to pull it from a registry. That registry could be Docker Hub or it could be your company's private registry. Once the image is downloaded, Docker can use it as the blueprint for creating the container. And this brings us to a very important Docker concept: images are not containers. A Docker image is basically a blueprint, and that blueprint is built using layers. You might have a base layer, then libraries, then nginx, then configuration. These layers are generally immutable and can be reused. And that's one reason Docker images are efficient. If two images share the same base layers, Docker doesn't need to download everything twice. It can reuse what it already has. So remember this simple analogy: images equals to blueprint. Containers equals to running instance of that blueprint. Now, we go one level deeper. Meet Containerd. Containerd is responsible for container lifecycle management and works underneath Docker engine, creating containers, managing their lifecycle, working with image snapshot, communicating with the runtime. These responsibilities are handled at the lowest layer. A useful mental model is Docker engine decides what needs to happen. Containerd helps manage how containers are handled at runtime, and then we go even deeper. Meet runc. Runc is a low-level OCI compatible container runtime. This is where things get much closer to the Linux kernel. Runc takes the runtime configuration and actually creates the container process. It sets up namespaces, applies cgroup configuration, sets up the environment, and starts the application process. So if Docker engine is the manager, Containerd is coordinating the container lifecycle, runc is much closer to actually creating the process that becomes your container. But how does Linux makes a container feel isolated? One major answer is namespaces. Namespaces gives processes an isolated view of certain system resources. For example, process ID, networking, mount points. So a process inside a container doesn't necessarily see the exact same environment that you see from the host. And here is the important part. Containers are not running their own kernel. They are using the host's Linux kernel. So the mental model is same kernel, different views. Namespaces handles the isolation. But what about resources? That's where cgroups or control groups comes in. Suppose I have a container running an application with a memory limit of 512 megabytes without resource controls. One badly behaved application could try to consume huge amount of memory. Cgroups allow Linux to control resource consumption, CPU, memory, and other resources. So when the container says, "Give me all the memory," Linux can basically respond, "Nope, you get 512 MB only." And that is extremely important in production environment. And this brings us to one of the most important mental model in Docker. A container is not a mini virtual machine. With a VM, you are virtualizing hardware and typically running a complete guest operating system with its own kernel. With containers, we are isolating processes while sharing the host kernel. That's one of the reasons container can be much lighter and faster to start. So remember, VM virtualize machines and containers isolate the process. Now let's look at the file system. Remember those image layers? The container gets a file system view assembled from those layers. The image layers are read-only. When we start a container, Docker adds a writable layer on top. So if nginx creates or modifies a file inside the container, that change goes into the writable container layer. And here is the catch. When the container is deleted, that writable layer disappears too, which means Don't treat the container's writable file system as your database. So here comes, for persistent data, we use things like Docker volumes. Imagine a database running inside a container. The container can be deleted, recreated, upgraded, replaced, but you probably don't want your database data disappearing every time you recreate the container. That's where persistent storage comes in. The container is disposable. The volume holds the important data. So a useful DevOps principle is keep applications disposable, keep persistent state in persistent storage. Now our container needs to talk. Maybe it needs to talk to another container. Maybe it needs to talk to a database. Maybe users on the internet needs to reach it. Docker creates networking components to make this possible. Containers can communicate through Docker networks. Docker can create virtual interfaces and bridges, and ports can be published from the host to the container, which brings us to one of the most commonly used Docker option, port publishing. Let's say nginx is listening on port 80 inside the container, but we want user to access it through the port 8080 on the host. We can use -p 8080:80, which basically means host port 8080 maps to the container port 80. So the request comes in on host 8080, Docker forwards the traffic to container port 80, and nginx receives it. Simple on the surface, but underneath, Docker is doing networking work to make that path possible. So now let's understand container lifecycle. We can create a container, start it, it enters the running state, stop it, we can eventually remove it. Commands like docker create, docker start, docker stop, and docker rm interact with that lifecycle. And again, a container isn't a permanent machine sitting around forever. It's an isolated process environment with a lifecycle. Now let's put everything together. You type docker run nginx, CLI sends the request, dockerd receives it and coordinates the operation. Docker checks for the image. If it's missing, the image is pulled from the registry. Containerd manages the container lifecycle. runc creates the container process. The Linux kernel provides isolation and resource controls using things like namespaces and cgroups. Docker configures the file system and networking, and finally nginx starts. So that innocent little command you typed, there is quite a lot happening behind it. And here is where understanding architecture becomes extremely useful. Suppose Docker run fails. Don't randomly start restarting things. Ask which layer is broken. Is it the CLI or API? Check the command or connection. Is dockerd having a problem? Check the docker daemon. Can't pull the image? Check the registry or image configuration. Container isn't starting? Look at the containerd, runc, and runtime errors. Application is getting killed because of memory. Think cgroups and resource limit. Can't connect? Think networking. Data disappeared? Think storage and volume. And finally, if everything underneath looks healthy, maybe the application itself is the problem. Yes, sometimes Docker is innocent. So if you remember only one slide from this entire video, remember this one. You use the CLI communicates through the API reaches dockerd. Docker engine coordinates the operation, containerd manages container lifecycle operations, runc creates the container processes, the Linux kernel provides the actual isolation and resource control primitives, and finally your application runs. Around that process you also have images for the file system blueprint, networks for communication, and volumes for persistent data. So the entire story can be summarized as CLI asks, engine coordinates, runtime creates, kernel isolates, and app runs. And now you understand the basic Docker architecture. But there is one question we haven't completely answered yet. We kept talking about Docker CLI and the Docker engine. So what's actually the difference between them? what does the CLI do, what does the engine do, and why can you have a Docker CLI without a Docker daemon doing actual works. That's exactly what we will break down in the next video, Docker engine versus Docker CLI. So if you are following the Docker fundamental series, make sure you continue with that one. I'll see you there.